Hi, everyone. Good afternoon. Thank you for coming. This is Christine Ramdin from Department of Emergency Medicine, Rutgers, New Jersey Medical School. Today, we are introducing our second webinar in our Biostats Made Simple, Session 2. This is a continuation from what we were talking about in Session 1. We had a really great turnout last time, so we'd like to thank you for that. We have Lynn here in the crowd who helps me put this together, and she will interrupt should there be any questions. We hope to make this simple and accessible to everyone in the crowd and to help empower everyone to conduct their studies as well as use this as a foundation for any other work they want to do in the future. Please feel free to interrupt at any time. We're going to start with a recap of some of what we discussed last time, as well as introduce the concept of nominal variables, as well as what tests are used to compare groups of nominal variables. So our agenda today, we're going to start with a recap. We're going to talk a little bit about nominal variables, and we're going to talk about the tests that are used to compare groups of nominal variables. These include the chi-square difference of proportions test, and then when it doesn't work, as you'll find out later, the Fisher's exact test. Then we'll kind of group everything together and give some final takeaways. So if you remember at the very beginning of our presentation last time, we spoke about three types of variables. They are continuous variables or scalar variables, nominal variables or categorical variables, which will be the focus of our presentation today, and ordinal variables, which are your Likert type scale variables. So just for a quick little visual, here are examples, again, of our three different types of variables. Nominal variables, as you can see from the screen, include variables that have categories such as colors, gender, race, ethnicity, etc. Scalar variables are your continuous variables like age, height, temperature, etc. Ordinal, again, are like your Likert scale data, your educational levels, since education can go from like K through 8, but you don't find decimal points in between. It's just K, 1, 2, 3, etc. And customer satisfaction ratings, because we generally rate them from 1 through 5 or 1 through 10, etc. So these are the three different types of variables. Okay, one thing I forgot to mention last time. So I'm a little bit of a programmer, so my natural tendency is to automatically find commands for everything. So when I was teaching you all the last session about how to do basic stats in Excel, I automatically went to the commands. I selected the data set, and then I put equals median, equals mode, and selected the data set to find those values. However, at that time, I did forget, and many of you may have thought of this afterwards, there is also a descriptive statistics feature in Excel, which will automatically give you all the descriptive statistics you need for your study without having to manually calculate them yourself using commands. So here I have summarized the steps on the screen to install that particular tool pack. If you all have Excel right now, you can literally follow the steps because I actually do not have it installed on my Excel for that very reason. So I'm going to install it in front of you guys and you guys can follow along. So I'm about to hit stop share and I'm going to install that tool pack and show you guys how to use that descriptive statistics tool pack in Excel. So I'm going to hit stop share and I'm going to share my Excel. So as I said, if you guys have Excel open on your background, you can open it right now and I'll show you how to install this tool pack for your future use, because I'll be doing it lifetime as well. So I'm going to hit File, then I'm going to hit Options, then I'm going to hit Add-ins, and then on Add-ins, I'm going to hit Analysis Tool Pack. As you can see, it says inactive for maybe most of you all, and for me as well, because as I just said, I usually don't use this. I'm a programmer, so I naturally tend to use commands, but this is probably going to be a lot easier for everyone. So I'm going to hit Analysis Tool Pack. I'm going to hit Go, maybe. Yes, I hit Go. Then I'm going to click Analysis Tool Pack. Okay, I believe it should have installed. I'm going to go to Data. And here we go, Data Analysis. So prior to installing that tool pack, many of you and I also I did not have data analysis. Now we have that feature called data analysis. So now to test how that descriptive statistics feature works, I'm going to quickly generate some random data just like I did last time. So I'm going to hit equals rand between 1 through 100. That's going to give me a random number between 1 and 100. And then I'm going to drag that cell down to give me more random values between 1 and 100. And now I'm going to conduct a descriptive stat. So I'm going to select this data. I'm going to hit data analysis. And then you see there's an option here for descriptive statistics. I'm going to click OK. And input range, that's the data that you want to analyze. So this is our input range. I'm just dragging it down here. And then output range, that's the cells that you want the data output would be. Recall what this is going to do. It's going to produce us a list of descriptive statistics such as mean, median, mode, etc. of our current data. So whatever we specify as our output range will be the place where it outputs that data. So I'm going to click on the arrow, and I'm just going to click a random space on the screen. And then you see it selects that range. Now we could have also put this in a new sheet, but just to keep everything simple, I'm going to keep it on the same sheet. And I'm going to click on summary statistics. Notice to give you the confidence level for the mean. I'm going to click on that. And largest and smallest values, I'm going to hit OK. And if you were following along and you did the same thing, you probably got the same output or similar output to what I got. So as you see, this is a very simple way of getting all of your descriptive statistics for your sample without having to manually command everything. Notice it gives you standard deviation, etc., things I didn't teach you how to calculate the last time, but it's all readily available right here. So that makes that really easy and really convenient for you. Now, one thing I want to point out again here, there is no interquartile range reported here for whatever reason. So in that case, again, if you're just doing a basic stat study, I would use an online calculator. Maybe there's some complicated commands to do it in Excel, but I, generally don't report IQR unless the data is not normal. And we test for that, as I'll remind you about later. So if necessary, feel free to use the online calculator if you need the IQR for whatever reason. One thing I wanted to bring to your attention here, we talked about confidence intervals the last time. What Excel outputted here was our confidence level for the mean. This is confidence level, not confidence interval. What I will show you how to do, though, and you'll probably never have to do this, but for an understanding, I will show you how to do it, how to calculate the confidence interval for the mean based off this confidence level. So if you recall from our last presentation, I told you that the confidence interval for every parameter has a lower bound and an upper bound. The confidence level will help us calculate that lower bound and upper bound by adding or subtracting the level from the parameter of interest accordingly. So here our parameter of interest is the mean. So in order to find the lower bound of the confidence interval, what I'm going to do is subtract the mean from the confidence level. So we're going to hit equals the mean minus the confidence level. 35. So that's the lower bound to our 95% confidence interval. Now for the upper bound, we're going to add the confidence level to the mean. So we're going to hit equals the mean plus the confidence level. So that's our upper bound for the confidence interval. So the way we would write this, and this is how you see it reported in medical literature, open parentheses, lower bound 35.03, comma, the upper bound 64.4. Now again, I showed you a really simple way how to calculate the confidence interval for proportions, for example, in VassarStats. Later in the series, when we use SPSS, the confidence intervals will be manually given to you by the software. I just showed you how to do it here for understanding and, for ease of noticing and seeing these things and trying to understand what they mean. So that is that, and that's a really easy way to get all the basic stats you might need for this study. There is one other thing, a cute other little trick I wanted to show you guys. I know a lot of you, some of you do medical education research, and some of the data that you use is Likert scale, for example. So I'm going to show you a quick Q command on how to, calculate the frequency of each type of Likert scale value in a data set. That might be very useful for you, but I thought I'd show you because that's also a descriptive statistic. So I'm going to just generate some Likert scale data here. Okay, so we have a bunch of Likert scale data here from different students for some given question. And you want to know how many people responded 1. So a quick way how to do this is to use the command COUNTIF. So I'm going to hit equals COUNTIF, the range of cells, and you literally can just select the column A, comma, 1. That's our criteria. We want to see how many ones there are. So I'm going to close the parentheses. I'm going to hit enter. So it tells us in our data set, 9 people responded 1 to that particular question, whatever it was. And then the same thing, you can repeat it for 2, 3, 4, and 5, right? So is equal to COUNTIF, range of cells, comma, 2. So we have 11 twos. Same thing for 3, 4, and 5. And this is useful if you just want to know like the proportion of people that responded in a certain way to a certain question. So if we know we have a total of 57 respondents and we want to know how many people responded 1, we would just do 9 divided by 57. Approximately 15.8% of people responded 1. But that was a cute little trick I wanted to show you because I know oftentimes, you know, with the medical school education data, a lot of the times like it's in an Excel document and then you just need to know basic things about it. So that's just another useful command. I think that would be really helpful. So any questions or anything about Excel or anything that I talked about at this point? Did anybody get stuck or is anyone confused? All right, we're looking good so far. Thank you all for joining. Let's go back to my slide presentation. Okay, so again, these are just basic steps on how to install that analysis tool pack onto your Excel for easy analysis. I take you through here step by step. Again, this is being recorded and you will have access to the presentation after the recording. So if you didn't get to install the tool pack, all the steps will be here on the PowerPoint and the presentation. Okay, so that was a recap on some of the basic stats. Now, just to summarize, I mentioned one of the big things that came out from the last presentation was that, you know, all descriptive stats cannot be reported for all data sets. And the reason why is for continuous data, data could be normal, that's not parametric, or not normal, that's non-parametric. So data normality always needs to be tested for continuous and ordinal data. So in order to test for normality, we use something called the Shapiro-Wilks test. And I showed you a basic example how to do that on an online calculator. Shapiro's Wilks test could also be done very simply in SPSS. We'll get to that later down on the webinar, but there are, again, as I want to remind you, some online calculators that are trustworthy for those that haven't had much exposure to a lot of online software and they're just doing basic stats. A reminder about how to interpret the results of Shapiro-Wilks test. If the p-value, apologize for the typo, is greater than 0.05, your data set is considered parametric or normal data, in which case you can use all statistical tests for normal data. If your p-value is less than 0.05 or the data is non-parametric, then your data is considered skewed and you would have to use non-parametric statistical tests. For the sake of basic stats, that also affects how you're reporting the data. So for example, if you test your data set, the Shapiro-Wilks test comes back, p is greater than 0.05, that means your data set's normal, you would have to report your mean and your standard deviation. However, if the p-value is less than 0.05, that means your data set is non-parametric and you would have to report the mean and interquartile range. That's basically what it means for basic stats. It also dictates, again, what types of tests you use, such as the Mann-Whitney t-test, etc. But we will get to that in another webinar. Today, our focus is on tests used to compare groups of nominal or categorical variables. Again, as if you may remember from the last webinar, one of the things I said was that you cannot use the same statistical tests to compare continuous and ordinal variables as you would nominal or categorical variables because they're two different types of variables. So again, examples of nominal or categorical variables are several of those examples you see on the screen. That includes gender, and you see that gender is broken down into several different categories, the same as race, the same as color, political party. So now just to kind of bring this in perspective, I present an example question. So I have 2 bags of colored marbles, and I know both contain the same colors. And I know the frequency of each type of color in each bag. And this frequency distribution we present here to the left. As you see, we have this broken down into bag 1 and bag 2. And we have the type of each color marble represented here in the table, as well as the total number of marbles in each bag. My question is there a significant difference in the number of yellow marbles between bags? Now, if we look at the numbers here, again, our question is focused on yellow marbles. And just looking at the numbers, we see bag 1 has 15 yellow marbles, bag 2 has 18 yellow marbles. We notice the total for bag 1, however, is 30 marbles, and the total for bag 2 is 36 marbles. If the denominators were the same, we can obviously say that bag 2 has more yellow marbles than bag 1. However, since the number of marbles in each bag are different, we cannot easily make that conclusion. We can do a proportion and, look at the proportion and, determine whether the proportion in each is one proportion is greater than the other, but how do we evaluate that for statistical significance? How can we say that one bag significantly has more marbles than another bag? And if you noticed here, this is going to become a little bit more clear in the next few slides, but I highlighted the piece where I ask whether there is a significant difference versus something else, which I'll talk about later. And that's going to become very important when we talk about p-values. So how do we go about, is the question, calculating the difference in yellow marbles between bags when the denominators are not the same? How do we determine whether the difference is statistically significant? And that's what we're going to get to right now. So when we're in that unique situation where we have two groups of people, two groups of things, and there's one group that has a particular characteristic or particular parameter and another group that has the same parameter, but there's a difference in numbers, and you want to evaluate whether there's a statistical difference because there's a difference in denominators, you use something called the chi-squared difference of proportions test. So we're going to go back to our example. Now, one way to use the chi-squared difference proportions test is to use it on an online calculator called VassarStats. I had stated in my previous presentation, VassarStats is one of my favorite calculators, and it's trustworthy because it has links and references. However, you do not need to, if you do not feel comfortable using VassarStats later when we talk about SPSS, we can show you how to do the same things in SPSS, and you can use that moving forward. However, typically, if you're just doing an abstract or whatever, and you want to do a quick calculation, and you're not concerned about reporting what software you use, trustworthy online calculators such as VassarStats are simple things that can be done quickly, and, it's easy for you to use. So now I'm going to stop sharing and repeat this example in VassarStats so you guys can see. So I'm going to write this down so I don't forget the numbers. So in group 1, we have 15 out of 30 yellow marbles. And in group B, we have 18 out of 36 yellow marbles. So if you guys want to open your internet and open up VassarStats as well and follow along, that's completely fine. All right, so I'm going to go to on VassarStats. On the left-hand corner, I'm going to click on proportions. I'm going to click on the significance of the difference between two independent proportions. That is the chi-squared difference of proportions test. And then before I input any values, so I lose no one here, I'm just going to explain to you what you're seeing here. So we see sample A and sample B. In context of our problem, sample A is bag 1 of the marbles, and sample B is bag 2 of the marbles. Our K is the frequency of our parameter of interest in each bag. So our KA is the number of yellow marbles, number of yellow marbles in bag 1. And our KB is the number of yellow marbles in bag 2. And our NA, and I'm sure all of you have seen N at some point, N is our total, right? So our total number of marbles in bag A was 30, and a total number of marbles in bag B was 36. And that is all you have to input into this calculator. So I'm just going to input it now. Again, for refresher, KA is the number of yellow marbles in bag 1, which is 15. NA is the total number of marbles in bag 1, which is 30. KB is the total number of yellow marbles in bag B, or bag 2, which is 18, and NB is the total number of all marbles in bag 2, which is 36. So again, n's are your totals, k is the frequency of the parameter of interest. Again, our question is, we want to know if the number, is there a difference? Again, that question of whether or not there's a difference in the proportion of variables in bag A compared to bag B. So that's all you have to input here. I'm going to hit calculate. So you see output here. You notice that for bag A, this is PA is simply the proportion. That's your decimal. It's 0.5. In bag B, it's also 0.5. And down here, your probability are your p-values. This is all what it means. And you notice here, there's a one-tailed p-value, and then there's a two-tailed p-value. And this is why I highlighted that piece of the question that stated, is there a difference? And the reason why is because the question you ask determine what p-value you use, whether it's a one-tailed p-value or a two-tailed p-value. For clarification, for two-tailed p-values, the question you're asking is whether there is a difference. Think of it as your non-inferiority trial, right? You're not trying to prove whether something, one drug or whatever it is superior to another. You just want to know if there's a difference, and you're just hoping that there's not a difference. For one-tailed, the p-value, the question you're asking is the number of yellow marbles in one group significantly more than the other group. So the p-value you report in whatever study you're conducting is dependent on the question you're asking. Recall again the question we're asking here, is there a difference? So we're not looking at one-tailed p-values here. We're not asking, is one group greater than another? We just want to know whether there's a difference in general. Notice the two-tailed p-value here is a 1. And we know from our previous lecture and your knowledge in general, whenever the p-value is greater than 0.05, which is the cutoff we established, there is no statistically significant difference between groups. Therefore, we can conclude in our question, between bags, there is no statistically significant difference in the number of yellow marbles. Okay, I see a comment in the chat. I've always used MedCalcX on my phone for doing this calculation. I find it helpful for several reasons. It is on my phone and available all the time. It gives relative risk, odds ratio, adjusted relative risk, number needed to treat with their confidence intervals. Can do this 90 for 599 CI. It always calculates a two-tailed test. Any others used or had uses with the experience? So this is an excellent question. See, I'm a PhD, so I don't use MedCalc. I may have heard of it before, but I've never used it. And I'm pretty sure if most of the medical community uses it, it's probably something reliable to use. But if anyone has any questions, feel free to ask. But I'm sure if this is something that's used and it gives you everything easily, feel free to use it. Thank you, Dan. All right, so just again for re-emphasis in that example, when you're using VassarStats in particular, probability means your p-value. And one-tailed or two-tailed refers to the p-value of interest. So again, for two-tailed, you're asking whether there's a difference in general. You're not caring if one side is significant than the other. One-tailed is whether you're asking the question whether one bag has significantly more marbles than the other. With that being said, we move on to the next example where we would utilize a one-tailed p-value. So I conducted an RCT to examine the effectiveness of Tylenol in reducing pain due to headaches, which is my group 1. This is my group that is taking Tylenol. And we wanted to compare headaches after 2 hours compared to the placebo. So placebo group did not receive Tylenol. They received something that may have looked like Tylenol, but it's not Tylenol. So we have our frequency table again here. One group that reports headaches after 2 hours, and the other group that reports no headaches after 2 hours. Our group 1 is our group that was given Tylenol. Our group 2 was our placebo group. So again, just like our marbles example, we have 35 people total that was in group 1, and we have 30 people here that's in group 2. Again, if the denominators were the same, we probably could just look at the numbers and say that, hey, group 1 has a greater number of no headaches compared to group 2. But that's not the case. We have different denominators. So let's go to our question. Our question is asking, is the proportion of patients that reported having no headache, that's this column right here, in group 1 after 2 hours, significantly greater compared to those in group 2? So this is why these frequency tables are so important if you're doing these problems or if you're trying to solve your own problem. You can easily get lost in words, and that's why we have to put this down in perspective, and this is going to be very helpful when we use another calculator in our next few slides. So we see here for interpretation, group 1, after 2 hours, 15 people reported headaches. That's the group with Tylenol. And group 2, after 2 hours, 20 people reported headaches. That's the placebo group. Our question is focused on those with no headaches. So we want to know whether there is a significant difference, a statistically significant difference, and the number of people or the proportion of people that reported no headaches in group 1 after 2 hours, that's the group with Tylenol, compared to group 2. So I'm going to write my numbers down here again because we're going to go through this example. So my KA here, that's A would be my group 1 or the people with Tylenol. And my parameter of interest is no headache is 20. My total in that group is 35. And my KB, my B is group 2. Those are the people with placebo. And the number of people in the parameter of interest, those are with no headache, is 10. And my NB, which is the total in group 2, is 30. Now we're going to go to VassarStats and do the calculation. All right, so let's reset the calculator. Our KA, again, that's the number of people in group 1, that's the group with Tylenol, that reported no headaches after 2 hours. That's 20 people. Our total number in that group was 35. KB was our group 2, that's our placebo group. The number of people that reported no headaches after 2 hours was 10. And the total number of people in that group was 30. And now I'm going to hit calculate. So looking at the proportions here, in group A, we have 57% of people that reported no headache after 2 hours. In group B, we have 33% people that reported no headache after 2 hours. That's our placebo group. So we're looking at this and, we can't obviously tell a statistic, like whether or not, we can tell there's a difference. We're not sure if it's statistically significant. So that's why we look down to our probability or our p-values. And notice again, we're presented with both our one-tailed p-value and our two-tailed p-value. Remember, VassarStats is not artificially intelligent. We're not putting it in a question here for it to analyze. That's our responsibility to look at our question and determine what is the appropriate p-value to use based on the question. So again, our question was there a significant difference in no headaches between groups? Now, was there a difference? Was there a significant difference in one group versus another? And let's just go back to that question quickly to emphasize that. So we wanted to know whether the proportion of patients that reported having no headache in group 1 after 2 hours significantly greater compared to group 2, or if it was significantly less. If that's the question we'd asking, it would be the same calculation. It'd be the same p-value we'd use. So again, if we're evaluating just whether there's a difference, we're looking at two-tailed p-values. If we're looking if one group has significantly more or one group has significantly less, we use the one-tailed p-value. In this case, our one-tailed p-value is 0.027, which we can round to 0.03. So yes, there is a significant difference, and there's the proportion of patients that reported having no headache in group 1 after 2 hours is significantly greater compared to group 2. So that's how you evaluate that for statistical significance. Another thing I want to point out here, how important it is to be genuine to your study question and put things in context, is if you accidentally report that two-tailed p-value, right? Notice it's 0.05, 0.0549 in fact. So if we were using the two-tailed p-value, we would conclude that there's no difference. But again, that is not our question. We want to know if one is significantly greater than the other. So that's why that's really important. Okay, another thing I wanted to bring to your attention. So remember the last time we were talking about confidence intervals versus p-values and how to kind of evaluate that, whether there's a statistically significant difference or not. So here I computed the confidence intervals for both proportions. So for group A, I had using VassarStats, 20 out of 35, and group B, I have 10 out of 30. Now, in this case, since there are only two parameters of interest, headache or no headache, I would use the confidence interval with continuity correction since our outcome is binomial, headache or no headache. Had there been 3 categories, in which I'll discuss later, there's scenarios where you can do that, you would use the 95% confidence interval with no continuity correction. So if we look at the confidence intervals here, we see that The lower bounds for group for the portion of people that reported having headaches after 2 hours, so group 1, is 39.5%, and the upper bound is 73.2%. If we look at the other group, the lower bound is 17.9%, and the upper bound is 52.9% approximately. And now, to evaluate statistical significance using confidence intervals, we kind of look at it and determine whether there is overlap. And we do notice that there is overlap between the two confidence intervals, right? So 0.5286, just looking at the upper bound of the second group, falls between 0.395 and 0.73. So if one were to use confidence interval here, the conclusion would be that there is actually no statistically significant difference between groups. So in summary, depending on what the journal asks for and things like your sample size, because one thing I wanted to point out again is, if you recall in my last presentation, I stated that, the smaller your denominators are, the wider your confidence intervals would be. You see that your confidence interval here extends from 17% all the way to almost 60%. So the confidence intervals are very, very wide. And that gives you a little bit more leeway. And in terms of when you're looking at overlap, had the sample sizes been larger, the result probably would have matched what the p-value gave. However, since the sample size is small, and that's why, and at that point, when people see conflicting results, they will ask, well, that was a pilot randomized control trial, right? Was it actually powered to detect a true difference when one existed? So that's an excellent question. Is 35 people enough? Or is 30 people enough to be able to confidently call that p-value statistically significant? That's one of the reasons why people have started, looking at it from both perspectives, from both p-values and the confidence intervals. So looking at it from both perspectives is really good for a larger perspective. It gives you, questions to ask about the study design, etc. And, looking at confidence intervals also tells you a lot about the data. Immediately looking at these, you see how big the intervals are. So, it gives you room to think about study design, whether or not am I correctly concluding there's statistical significance when there is not. So I just wanted to point out that very important question there. All right. So just again, since this is a really important point, wanted to summarize again. For chi-square difference of proportions test, or in any test in general, if you're just looking to determine whether there is a difference, you report two-tailed, the p-value for the two-tailed test. If you're testing whether one group had significantly greater or significantly less than another, then you would report the one-tailed p-value. And again, in scenarios where you would use this, why would you report a one-tailed p-value in a real clinical trial, right? If you're, in my example, if you're testing Tylenol or you're testing another effectiveness of a medication, you want to know whether this medication works better than the standard or better than what you're currently doing, right? So then you would use your one-tailed p-value. If you're in pharma and you're conducting a non-inferiority trial because you came up with this drug for a blood pressure medication, and it's, you want to test whether it works as effectively as a blood pressure medication that was released by another pharma company, but at the same time, yours is cheaper. So you think it's okay to put out in the market. You want to conduct something called a non-inferiority trial, right? Because you're saying that, look, I'm not trying to prove that my medication is better, but my medication is cheaper and it works just as well. So that's an example where you would use a two-tailed p-value. Did I lose anybody? Any questions at this point? Alrighty, awesome. Next, so we're crunching down now. So I have another scenario in which the chi-square difference of proportions test does not work for nominal variables, and I'll explain to you why. So here's the example. I have 2 bags of colored marbles. I know both contain the same colors, and I know the frequency of each type of color in each bag. Same scenarios as we started with. And we have bag 1 and bag 2, and we have our number of marbles in each bag. Notice, however, that the numbers that I'm reporting here are much smaller than the numbers that I initially reported. They're in the single digits. So my question here, is there a difference between the number of yellow marbles between bags? Again, bringing this back to one-tailed and two-tailed, we're just asking whether there's a difference. That means we're going to go for our two-tailed test, whatever test we decide to use. So I input this into VassarStats. And I'm not going to do it because I just have a screenshot right here showing it. So my yellow marbles in bag A is 5. The total number of marbles in bag A is 12. Number of yellow marbles in bag B is 3. Total number of marbles of bag B is 10. I hit calculate. VassarStats give me an error stating that at least one of your samples does not satisfy the requirement that NP and N1 minus P must both be greater than 5 or equal to. Now, many of you that have taken stats a long time ago in undergrad or in med school recall that there's this criteria. But today in the real world, when we're actually trying to do our stats and we have all these calculators, no one's doing this by hand. So you do not need to worry about this calculation before you put it into the calculator. My way around it is just put it in the calculator, hit calculate. If it gives you the error, immediately go to the alternative, which is the Fisher's exact test. So the summary here, you use VassarStats chi-squared difference of proportions test when comparing two groups for nominal variables. However, if the test fails, then you have to use something called the Fisher's exact test. And I'm about to show you that right now. Okay, so one of my, and I have to do this the online calculator way because we're not at SPSS yet, but again, I want to show you that, there are in fact, if you need to do a quick calculation, some online calculators are trustworthy. This is another one of my favorite calculators, social science statistics. And one of the points that was brought up in the last presentation, how do we know some of these online calculators are trustworthy? Well, the calculator itself, one of them, actually presented that data to you. So it says here, why should you trust these tools? The output of these calculators and tools featured on this website have been audited for accuracy against the output produced by a number of established statistics packages, including SPSS and Minitab. So you could be confident that you're not being led astray using our resources. So that makes me feel good as a researcher, especially if I'm a basic researcher, like I'm just, doing things. It's like a huge randomized control trial. It's an abstract I want to get out. And, I don't know how to use SPSS. So what do? You look for resources with these, pieces of evidence that you can be confident that they're trustworthy. However, again, we will show you how to do this in SPSS when we get there. So there's a calculator here called the Fisher's exact test calculator. And you see that immediately it asks you to put input in a table. And this is why I was emphasizing these tables were so important in the beginning. It's very important to get your labels and everything correctly so that you do not mess up the calculation. So I would always suggest whenever you're using this calculator, relabel your variables, and it allows you to do that. So your group 1 here would be your bag one of marbles, and your group 2 here would be your bag 2 of marbles, bag 2. Category 1 would be number of yellow marbles. Let's see if it takes the $, or you can just type in yellow marbles. And category 2 would be the number of marbles that are not yellow marbles. So it's going to be your total number of marbles in that bag minus yellow marbles or not yellow marbles. So I'm going to hit next, and it's going to ask me to input my numbers. So in bag 1, we had 5 yellow marbles. See, after a while, notice when I put in my output here, I didn't label the groups. When you're just starting out getting comfortable with it, I wouldn't suggest doing that. After a while, you just know what goes in and you do it, but I always suggest labeling your groups so you don't get lost. So for category 1, we had 5 yellow marbles in category 1. And category 2 would be the total in that group, and the total number of marbles in bag 1, which is 12, minus the number of yellow marbles, that's 5. So that's category 2 is 7. So category 2 again is number of marbles that are not yellow marbles. Group 2 is the number of marbles that are yellow in bag 2, which is 3. And category 2 are the number of marbles in bag 2 that are not yellow marbles. So the total number is 10. We subtract 10 from 3 and you get 7. So that's going to be our input into our calculator. So bag 1, 5 yellow marbles, not yellow marbles, 7. Bag 2, 3 yellow marbles, not yellow marbles, 7. So I'm going to hit next. See, by putting that input, the calculator automatically does the row totals for you. That's how you know whether or not you're doing this correctly. So, your total marbles in bag 1 is 12, as you know, and the total number of marbles in bag 2 is 10. So that's how you know you didn't mess up here. And then it gives you the option to determine what confidence level you want to select. Usually we report P equals 0.05. I'm going to hit calculate exact chi-squared, and it produces your p-value. It says that the exact test value is 0.67, and it also tells you that it's not significant, which you all are aware. So therefore, we can conclude that there is no significant difference in the number of yellow marbles between bag 1 and bag 2. Okay, so just wanted to, that was a lot. And then everyone's probably asking, why are you showing me this? Like outside of doing this is like seems so simple. Like who does this? Why do they do it? But other of you that, keep up a lot with the medical literature, notice that these things are used everywhere. These tests, chi-squared, Fisher's exact test. And all 4 of these examples I selected, all 4 of these are randomized control trials. And their primary outcome was assessed using the chi-squared test or the chi-squared and the Fisher exact test. See? And again, the reason why in this example, the second example here, the left corner of the slide, the bottom corner, they used Pearson chi-squared and Fisher's exact test. And the reason why they would do that is just for what I showed you in that example. When the criteria is not met for the chi-squared, you have to use the Fisher exact test. So these tests are used everywhere, big and small, etc. So it's really good to know them and understand when they're used. So final tips and takeaways. In summary, during this presentation, I showed you that there were several other ways to do descriptive statistics on Excel besides what I showed you in the earlier presentation. Now, if you're, some of you do have background in programming, and if you feel comfortable just typing equals mean, equals median, equals mode, you could do that. But, that is more time consuming than just clicking descriptive statistics and see what Excel has to give you. Also recall that you cannot use the same statistical test to compare nominal variables between groups as you would continuous or ordinal variables. Those tests for comparison will be discussed in a future webinar. Today, we just focused on how to compare nominal variables, to compare groups between 2 groups of nominal variables. Our chi-squared difference of proportion test is our primary test used to compare differences between groups or proportions. When that does not work, the criteria is not met, VassarStats give you an error, you have to use the Fisher's exact test. Now, you might also wonder that, what if I have 3 groups of people, not 2 groups of people? Then what do you do? Now, that is rarely done. You may notice, though, that, it has started to become a little bit more common in the literature. I'll give you an example. Recently, we published a study, comparing knowledge of MOUD and naloxone and perceptions of MOUD, etc., between 3 groups of people, between those that were substance users, those that were connected to someone that was a substance user, or those that had no connection to substance user. So you can easily see how we have 3 proportions, 1 for each group, and we would have to compare them. Obviously, in that case, you cannot use the chi-squared test or the, Fisher's exact test. There are extensions to those tests which you could use, such as the Friedman-Halt, etc. There's also this other scenario where you would use, such as you have the pair t-test, you have participants before and participants after. In that case, you have the same population of participants, and you want to kind of connect those dots. You don't want to assume that those proportions are independent. In that case, you would use a test called McNemar's test. And, that's not frequently used in the literature as well, but I just want to let you know that exists. And I'll give you a quick example of where I used that recently. So we published a study looking at changes in alcohol use at intake and 6 months after a peer navigator intervention. And so obviously we had all the identifiers of the patients, and we could actually link patients before and after. So we could do a matched analysis. In that case, we use something called the McNemar's test. So, those are very unique scenarios, like when you have 3 or more groups, or you have 2 matched groups, then you would use those tests. But you would notice that more of what's used in the literature is the chi-squared test and the Fisher's exact test. So being comfortable with those tests, reading and interpreting, even when reviewing, or, putting together that abstract or paper that you want to submit really quick, just be confident that these tests are widely used, and there's certain criteria for using them, and it's really easy to use them and use them correctly. So that was pretty much it I had to offer today. I hope I didn't lose anybody. I think we would, be open to take any questions. At this point, we'd be more than happy to answer.
This is wonderful, Christine. Thank you so much. You're very thorough, and I think you're thoroughness in teaching has provided us with like not needing to ask you any questions, because I think this is stuff that I think anybody listening to this can do some of this on our own, which I believe is the overall goal for these sessions. So thank you so much. We appreciate all your time.
You're welcome. I really appreciate that, Lynn, and I'm more than happy to serve the EM community in any way I could. So thank you guys. If you have any questions, feel free to reach out. Again, the recording will be available online. So thanks again. And again, feel free to reach out if you have any questions. I see Lynn provided her email and you guys can reach me as well. Thank you so much. Have a wonderful day.